So for the first research fundamentals tip for 2023, I'm going to introduce you to the most basic stats there are, which is descriptive statistics. So descriptive statistics are the basic ones that just summarize the data from a research study, whereas the inferential statistics, they're the scary ones with the crazy formulas and the terminology that you don't know how to pronounce and the p-values and things like that. So I'm not going to talk about them at all today. We'll save that for the next quantitative study that we talk about. But today we'll just focus on descriptive statistics. So basically descriptive statistics give you a clear picture of what the data is showing, just that one data set from the study. But if you want to be able to make like bigger, bolder statements about how, what the rates of something might be worldwide, or whether a particular intervention is going to be effective for like a population beyond just the people that you're treating, that's when you need to do the fancy stats tests, and they call that inferential statistics, where you get p-values and things like that. So this one was a nice introduction beginning article for you all, hopefully. And we'll worry about those inferential statistics and p-values another day, because there's none of those in this article. So for today, I just wanted to talk you through 3 of the main descriptive stats that you might see reported in a journal article. And I'll try and give you a few sort of basic examples to talk you through them, which might seem a little bit funny as we talk through this, but then on the next slide as well, I'll actually take you through some examples that they've got in the article and show you how we interpret it that way, basically. So firstly, we'll talk about the mean, which is basically just the average score. So for example, say we've got all the OTs in a particular workplace, and we'll say there's more than 2, so there's about 10 OTs in a workplace, and we want to find the mean score of their heights. So that's just finding their average score. So everyone knows how to do an average. Usually you just write down all the heights of the OTs in that workplace, add them up, and then divide them by how many OTs there are, and that's how you get your average height. The next one down there is the range. Again, nice, pretty simple to get your head around, where you're basically just looking at what's the difference in height between the shortest person and the tallest person, or in this case, the lowest to the highest height in centimeters there. So to find this, you just take away the lowest number from the highest number, and that will be the range. So for example, if the tallest OT was 190 centimeters and the shortest was 150 centimeters, then the range would be 40 centimeters. So the reason sometimes you'll see that in journal articles is just so you can see how much variety there was in the scores. Was everyone getting a really similar score, or was there lots of, big differences between the highest and lowest? And then finally, the standard deviation, which is where that scary looking curve thing comes in. It can be a little bit scary if maths isn't your strong point. So I'm not actually going to tell you how to do the calculation. You can Google it and work it out using square roots and things like that if you want to do it, but I'm not going to talk about that today. Today, I'm just going to tell you what it actually means. So the standard deviation is an indication of how variable all the scores are in a data set. And they come up with it by assuming that most scores will fall under this bell curve, where kind of like most of the scores are in the middle range or close to the average, and then there'll be less scores that are really at that high end range and less scores that are really at the low end range. And that's what they call normal distribution, basically. So in the diagram, if we look at the center line, which is right there where there's a 0 there, that's basically telling you what the mean is, or the average is. And then you can see either side of that, there's a line that says -1 and 1, and that indicates a standard deviation. So what they do is when they work that out, they can calculate the standard deviation, and it tells you that you can see that there's 34% in that shaded blue area. Basically, within a range where it's a standard deviation, either 1 below and 1 above the mean, about 68% of the scores, or 2/3 of people, are going to fall between those 2 lines. So again, if you want to find what are the majority of people sort of falling under, you look at the mean and the standard deviation. And don't worry, I'll talk you through this in a second. So if we go back to the height example, so say the average height was 170 centimeters for the OTs, and the standard deviation, once you worked out all that calculation, was about 10 centimeters. So this means that 68% of the OTs in that workplace are going to be between the heights of 160 centimeters, which is that 1 standard deviation, or 10 centimeters less than the average, and between sort of 160 and 180. So 180 was the 1 standard deviation higher, which was the 170 plus 10 centimetres. So if the standard deviation was actually only about 3 centimetres, then you'd be saying that 68% of those OTs are between the height of 167 and 173. So you can see that the scores are really much closer together, and there's less variability because that standard deviation is smaller. So basically what you're looking at when you're reading it in an article is how big is that standard deviation compared to the average score, and that will tell you, are they really spread out, or are most of the scores really close to the average? So I'll show you what that looks like in the article now, and then you can tell me to go back if it still is not quite making sense, but I think this sort of explains it a bit better. So this table is from table 2, and I've just cut out a chunk of it because it was quite a long table. But if you can see in the circle at the bottom there on the slide, it tells you that the data is presented as a mean plus or minus the SD, which is standard deviation. So if we go back up to where the top arrow is there, which is next to the age, the first number there is 45.4, and that's just basically telling you, so that was the mean, or the average age of the people in this study. So if you're trying to work out, is that months or years or something like that, because sometimes pediatrics, they might report things in months rather than years. You can see after where they've written age, they've got Y, so that means years. So you can tell that it's 45.4 years is the average age of the people in the study. And then you can see there's a plus or minus 14.2 after that. So this means that the standard deviation for this group was 14.2 years. So if we think back to that little bell curve on the previous slide, 68% of people, or 2/3 of people in this study, were between the ages of about 31 and 59 years old, because basically if you've got 45 and you take away 14, that's 31. You've got 45 and you add 14, that's 59. So that's a fair bit of variability in the age. So even though the average age was 45, it doesn't mean that majority of people were pretty close to 45. That sort of 2/3 of people were anywhere between the ages of 31 and 59. So it's a bit of a variety there. And then just another example to show you is a time to presentation. So again, you can see the D in brackets, so that's just telling you that it's days. So the average days from when they had COVID to when they're actually seen in the clinic was 93.4 days. So again, about 3 months or so. And then the standard deviation was actually really quite big, so it's 65 days. So this is telling you that about 68% of people who came to the clinic were anywhere between 28 days or 158 days post their initial COVID infection when they came. So that's either about 1 month or 5 months. So you can see that's a really big range. So again, it's not just because the average was sort of 3 months that they were presenting. People were presenting with difficulties 1 month and even up to 5 months or longer after their initial infection. This, like I said, it just tells you what they were looking at in their particular group of 100 people. They haven't taken it further and done any more stats tests where they'd have a p-value that you can say, oh, that must be 45 must be the average age for everyone with long COVID across the world. They haven't done that level of analysis. This is just to give you a bit of an idea of within their group what they were looking at.